Hello students. So in the previous video session, we have seen what do you mean by expectation maximization algorithm. At the same time, we saw what do you mean by maximum likelihood estimation, the problem of latent variables or hidden or unobserved data was tried to solve by maximum likelihood estimation. And in maximum likelihood estimation, we were supposed to know two things, that is the probability distribution function and the parameters of this probability distribution function. But how do we find these parameters was once again a question mark, and therefore we made use of expectation maximization algorithm or EM algorithm. We saw the 4 steps in EM algorithm. The first step was we were considering the incomplete or observed data, and our assumption was that it was coming from a specific model. Then we were applying the E step, and that is we were doing the guesstimation or estimation of the missing value, and then we were applying the M step, that is the maximization step. And step number 2 and 3 was carried out until convergence was met. We also saw what were the advantages, disadvantages, and applications of expectation maximization algorithm. Today, we will be seeing some more comprehensive information about expectation maximization algorithm. So, EM algorithm provides a general approach to learning in the presence of unobserved variables. Your unobserved variables are nothing but hidden variables or the latent variables. In many practical learning settings, only a subset of relevant features or variables are observable. So as we all know that if only a certain set of variables are available and others are hidden, it leads to inconsistencies. Some of the examples that fall under the category of EM algorithm are nothing but HMM, Bayesian belief network, and Gaussian mixture models, GMM. We have also seen this particular information in our previous video session. So, a way to find MLE, maximum likelihood estimation, for model parameters when your data is incomplete has missing data points. That is nothing but unobserved latent variables. Your MLE can find the best fit for a set of data, but it doesn't work well for incomplete data. That is why we are using EM algorithm. We have seen the 4 steps in the previous session. This slide is just a recapitulation of what EM algorithm is. These are the applications which have already been covered. Okay, so there is a numerical where we will try to find out the maximum likelihood estimation. Given an unbiased coin with equal probability of landing heads as well as tails. So there is an unbiased coin and the probability is equal. That means for a coin, for head to occur and for tail to occur, the probability is same, which is nothing but 0.5 for head and 0.5 for tail. What is the probability of observing the given sequence? Sequence is denoted by capital S and the sequence is given to you. You have to find out the probability of observing the given sequence. Head, head, tail and head. So let us see how we apply maximum likelihood estimation. So the distribution over here is a binomial distribution because it is an unbiased coin and it is given that the occurrence of head and tail is equal. So the sequence is given and P stands for the probability of head to occur. So the probability of head to occur or the overall probability for this particular sequence is 0.5 raised to the total number of instances. So it is 4. So the final answer is 0.0625. Now, if I'm considering a biased coin where P is the probability of heads, which is 0.7, then what will be the probability of observing the same sequence? So in that case, what will happen? We have seen binomial distribution, whereas in this case, the sequence remains the same, but it is a biased coin where the probability of head is 0.7. So we will be writing 0.7 raised to 3 because head is occurring 3 times into 1 minus P, that is 1 minus probability of head occurring is nothing but tail occurring. So 1 minus P, which is 0.7 raised to tail is occurring only once. So the final answer is 0.1029. So the aim of maximum likelihood estimation is to find the parameter values that make the observed data most likely. And in other words, given the observation, what should be the value of P so that P of S, given that P is taken place, is maximum. So basically, the aim of MLE is to find the parameter values that make the observed data most likely. Suppose the value of P is not known and we have to estimate it given the observation. Since the probability of heads is P, we know the probability of tails will be 1 minus P. So in the previous slide we saw P value was given, and if suppose P is not given, then how will you estimate it for a given observation? For binomial distribution, the likelihood or the probability of the observed sequence of the function is given as. Now here only the sequence is given, the probability is not given for binomial distribution. So what is it? It is nothing but P, that is the number of heads raised to 3 times head is occurring into 1 minus P, that is for tails. Here it should be raised to 1. Here 1 is missing. Alright, because tail is occurring only once. Probability of the observation as a function of the unknown parameter. How can you observe it? The goal is to maximize this quantity. So we have got P, that we can have what values of P, and what is the observation? Probability of S, the given sequence or observation, and we know P for different values of P. So this is nothing but the cos-toin probability, where we have got P raised to 3 into 1 minus P raised to 1. 3 represents the number of heads and here raised to 1, 1 represents the number of tails. There are many possible ways the above function can be maximized. If the function is too complex, then we normally use numerical algorithms to estimate the values of the parameters. But for simple functions like the above one, we can find a solution by setting the first derivative of the likelihood, that is of the probability, with respect to the unknown parameter. Your unknown parameter is p. So we can differentiate or carry out first order differentiation with respect to p on this particular function, that is p cube into 1 minus p raised to 1. Sometimes the function may be having local optimum, that is local maxima and minima, and hence the solution obtained may not be globally correct. We may not reach the global optimum, we may be stuck at local optimum. So this is a bit complex curve. As you can see, we may be stuck over here at the local optimum, and this is not the actual solution because we have not reached the global optimum, that is the global maximum. Maximum likelihood estimation, since we are dealing with probabilities, that is the number that lies between 0 to 1, raising them to exponents and taking the products will result in integer underflow. So we cannot take exponential values. So we can overcome this by simply taking the log of the given function. So what is done? So we know that the probability for this P, which is not known to us, and S is the observation which is given. Instead of using exponential values, we are simply using log. So log of this particular function is nothing but, what was this? This was P cube into 1 minus P raised to 1. So this is nothing but now 3 into log p, because p cube, if you are finding the log, it is 3 log p, and 1 minus p raised to 1. Log is nothing but 1 into your log 1 minus p. Now what are we doing? We are finding out the first order derivative with respect to the unknown quantity and setting it to 0. Here the unknown quantity is p. So what is it? We will be getting, when we find out the differentiation of 3 into log p d by dx with respect to your p, and here d by dp with respect to your log 1 minus p. So on applying first order differentiation, we get 3 into 1 minus p is equal to p, and we are equating it to 0. So solving this, we will take this 3 inside. So 3 minus 3p is equal to p. Minus 3p on the other side goes, it becomes 4p. And therefore p is equal to 3 by 4, which is 0.75. So we saw initially the value which is there for p was 0.5. And now the probability has increased to 0.75. So every time we calculate, we are trying to reach the optimum solution. Thank you.